I'm Srishti, and today I will be discussing my final year project, Emotion Profiling using Deep Learning. The motivation of this project comes from the use of emotion recognition in emotion regulation therapy as a psychotherapeutic approach. To understand emotion recognition, we need to understand arousal, which is a measure of how energetic we feel, and valence, which is a measure of how positive we feel. All the emotions can be classified into an arousal and valence pair, as shown in the table. The applications of emotion recognition include cognitive behavior therapy, emotion-focused therapy, and diagnosis and treatment of mood disorder. Brain neurons contain ionic content, which creates voltage fluctuations. EEG measures and plots these voltage fluctuations into signals. We reviewed literature to investigate the relationship between emotions and the rewarding nature of music listening. Here are a few popular datasets which have been used in literature. As you can see, the two most popular datasets use music videos as the stimuli. However, since we are focusing on audio stimuli as a form of music therapy, we would want to understand how can audio stimuli be used to vary the arousal and valence experienced by humans. This brings us to our research question: how do we analyze the changes in brain activity using EEG signals as a response to audio stimuli to understand the precise values of arousal and valence experienced? We hypothesize that the EEG features extracted using audio stimuli will be less prominent than those of video stimuli, and thus, the existing state-of-the-art neural networks will need to be improvised to account for the subtle features. Our research methodology involves the development of an interactive system, followed by data collection of EEG signals. This data is then pre-processed and analyzed to understand if emotions were induced. Finally, we train a neural network model and compare it with existing state-of-the-art models. The experiment is designed to include 13 arousal and valence classes as shown in the graph and the table. The experiment is conducted on 20 participants, all of whom participate in 2 sessions. The experiment of each session is divided into 3 blocks, where every block contains 13 trials, one from each of the chosen arousal and valence classes. Following every trial, we have a minimum 15 seconds rest. We collect 2 types of data: objective feedback, which is the EEG signal data collected as a response to the stimuli, and a subjective feedback where the participants analyze their emotions and report them on a 9-point self-assessment mannequin. The music is generated using AMGS system, and this is an Ableton screen showing the music generation. We now move on to the experiment interface demo. We start by entering the unique participant ID, selecting the session, and starting the experiment. The participant selects how they are feeling before the experiment to give us a baseline of the pre-experiments. The participant then goes through a sample UI, adjusts the volume, and is instructed how to give feedback post a trial. Once the participant has familiarized with the UI, there is a short break where the participant listens to nature sounds to clear his previous emotions and set him for a fresh emotion induction experiment. The participant then provides subjective feedback on the self-assessment mannequin as shown. Here is a system design. First, we use bandpass filtering to reject the signal frequencies which lie outside 0.3 Hz and 40 Hz range. Next, we normalize the data to offset factors such as electrode placement, subject variability, and electrical interference. Here is the pseudocode. We then augment the data using segmentation. Finally, we use decimation to reduce sampling rate from 1000 Hz to 250 Hz. We analyze the alpha band power of frontal channels. The plot here shows our analysis. We conclude that there is a positive correlation of the mean band power with the arousal and valence values. This confirms that emotions were induced as a response to the external stimuli. The plots here show the positive correlation which we have observed between the subjective user feedback and the true labels of our data. To classify the emotion states, we use TSEption, which is a state-of-the-art deep learning framework for EEG signal classification. TSEption uses a temporal learner and a spatial learner. The temporal learner employs a multi-scale convolution kernel, enabling it to acquire several discriminating temporal and frequency representations. The spatial learner, on the other hand, employs neuroscience findings and takes into account the spatial asymmetry of the two brain hemispheres when responding to emotions. Here is the structure of TSEption. When applying TSEption, we hypothesize that the maximum difference in the EEG signal is at the extremes of the arousal and valence axis. We thus vary arousal and valence and experimented with 4 combinations which are elaborated further. Our first classification was arousal 1 versus arousal 0. The results are shown. Our next classification is varying valence 0 with valence 1. This classification achieved a maximum accuracy of 69%. We next classify classes with arousal and valence 0, respectively, versus classes with arousal and valence 1. Lastly, we classified the classes with arousal less than 0.5 versus the classes with arousal greater than 0.5. Here is a summary of our results. The scope of this project involves the designing of a unity-based interface, using it to collect data from 20 participants and analyzing this data. The analysis of both subjective and objective emotion profiling data confirms that the participants of this experiment experienced emotions induced as a result of the experiment. We achieve accuracy of greater than chance level for most subjects with a maximum of 69% for the valence classes. Frontal alpha band power shows a positive correlation with the arousal stimuli. Comparing the results with state-of-the-art, we infer that the features corresponding to emotions are subtle and the difference in their emotion profiling EEG dataset. Hence, more efficient decoding networks are required to extract distinct emotion features and classify them with higher accuracy, thus confirming our hypothesis is valid. In future, we want to add an attention layer to the network and also extend the network to understand a spectrum of emotions more precisely using a regression model. Both of these will allow us faster diagnosis and treatment of mental health diseases. Thank you.